I'm Lucy Handley. I do the adult programs here at the Ridgefield Library. And I guess I don't have to say that this is part of the library's scholarly series, The Curious Mind, made possible by the generosity of the friends. Tonight's speaker, Dr. Heidi B. Hammel, has been a planetary astronomer for over 35 years and spent many of those years in Ridgefield. It was during that time that she joined the James Webb Space Telescope Science Team. She received her undergraduate degree from MIT and a Ph.D. from the University of Hawaii. She is currently the Vice President for Science at AURA, an organization that operates large astronomical observatories for the United States government, including the Hubble Space Telescope, JWST, the Gemini Observatory, and many more. Dr. Hammel primarily studies outer planets, but her work has spanned much of the solar system. She served on the imaging team for the Voyager 2 Neptune encounter in 1986 and led the Hubble Space Telescope Team to observe the Shoemaker-Levy 9 impact with Jupiter in 1994. In 2002, Dr. Hammel was selected by NASA to be a JWST Interdisciplinary Scientist with a program focused on observations of our solar system from near-Earth asteroids out to the Kuiper Belt. In 2020, she received the American Astronomical Society's Masursky Award for Outstanding Service to Planetary Science and Exploration. And in 2023, NASA awarded Dr. Hammel an Exceptional Public Service Medal. Asteroid 1981 EC20 has been renamed 3530 Hammel in her honor. Welcome, Dr. Hammel.
Hello, everyone. Super hot. Wow, maybe I'll move it away from me. It's wonderful to be back here in Ridgefield. I did live here for a long time, and I think that the very last talk I gave here in Ridgefield was a fundraiser to build this extension of the library. So it's just kind of fun to come back full circle. A lot of the stuff I'll be showing you when we get to the solar system section of this talk was actually planned here in Ridgefield at my home on Sarah Bishop Road, and one of my Sarah Bishop neighbors is here. So it's like old home week here. It's fun. And it's great seeing a lot of my friends and colleagues from that period of time. So I'm here today to give you an update on the James Webb Space Telescope. And I will start with the conclusion. Oh my God, turn this off. There. How awesome it is, and everything is really well. We actually, can you turn the spotlight off too, Lucy, when you get a chance? You don't need.
Yeah,
Yes. I'm afraid to touch this, but
You're talking, Heidi.
I'm going to try it. All right. So we do actually have fuel for more than 20 years worth of observations. And we are currently in the 3rd year, can you believe it? It's been up there for 3 years already, of its 5-year prime mission, but we can, like I said, we have fuel to go on and on. Okay, so let's talk about light. I already gave you the preview of this. We talked about the electromagnetic spectrum and all these kinds of light. And why this is important is because the universe emits light at all of these wavelengths, not just the visible part. And so we need telescopes that work at all of those wavelengths, and we have them. And JWST is specifically designed for infrared light. And why did we pick infrared light for James Webb? Why not visible light, like the Hubble Space Telescope? Infrared light has a lot of really important properties. Here's a visible wavelength image of 2 different kinds of animals, meerkats and a freshwater crocodile. This is what you and I would see with our eyes. But if we had infrared eyes or an infrared camera, this is what you would see. And from this, immediately you learn something, don't you? Why are the meerkats bright? They're warm. They're warm-blooded. Infrared light is warmth. And why is the crocodile dark? Because it's cold-blooded. So in this picture, you've learned about the temperature of the thing you're looking at. And we do the same thing in astronomy. Here's a picture of a constellation many of you know. I know my astronomer friends here know this. Orion Nebula. That's a visible wavelength light image. this doesn't have the blue lines in the sky. All right, but that's fine. But it's there as a guide because now I'm going to show you what Orion looks like in an infrared image. That's the same part of the sky. And what do you know from that image? What did you learn from the meerkats? Right, and so what do you know about this? There is hot dust here. This is dust here that you can see in the infrared, and you can figure out its temperature by how much it shines in the infrared light. And so these colors are super important for us. But JWST's absolute superpower is not the gorgeous pictures, which I'll show you. I love the pictures, but that's not its superpower. Its superpower is what we call spectroscopy. So what is spectroscopy? If you look at the rainbow of colors, and I show you here a visible rainbow, but it's true for infrared and ultraviolet too. Some materials will absorb certain wavelengths of light, preferentially. They'll just pick out that wavelength and that wavelength and that wavelength. It's because of quantum physics, and I'm not going to explain the whole thing to you, but trust me, it works. Other materials, though, depending on their pressure and their temperature, they can actually emit light at very specific wavelengths. You could think of these lines of extra light or missing light as fingerprints of molecules in space. And so by looking at these lines, we learn about the composition out there. Now, back in the olden days, and they said I've been a planetary astronomer for 35 years. 35 years ago, we didn't have printers that could print this sort of thing, right? So we had only black and white printers. So how do you print this in black and white? What we would do was sort of draw a line, and when there was extra light, the line would go up, and when there's missing light, the line would go down, and that, my friends, is a spectrum. And so what this thing, when I show you lines that look like this, is wavelength on one axis and brightness on the other axis, and by looking at the patterns of missing or extra light, we can learn about the chemistry. And not only the chemistry, we can learn about the temperature, the pressure, the dynamics, all sorts of things about things out there in outer space by looking at these spectra. And when we first started creating spectra, NASA would not allow us to show these. They said, you can't show those squiggly line plots. But we're trying to change all that with JWST because it's so amazing. Now here's an example of an exploding star called Eta Carina, imaged by Hubble. Very cool picture. Everyone loves it. But the astronomers, what they love is the spectrum. Because the spectrum, as I was saying, it tells you all the science stuff. So you can see that there's iron and nickel and argon and helium. You can trace all of that and trace its temperature, trace its dynamics by looking at the spectra. So I am not going to shy away from showing you guys spectra because you understand what they are now. Is everybody with me on spectra? Okay, good. All right, now here's another reason. This is actually the reason that we chose infrared. When you look at a nearby star, it tends to have hydrogen lines that we've named with Greek letters, alpha, beta, gamma, delta, epsilon. There's a few more over there. When you look at a galaxy, which is a thing that's composed of billions of stars, that's a little bit further away, if you look super carefully, you'll notice something. What do you notice? A little tiny bit of shift in the red there. That has to do with the expansion of the universe. And if you look at a much more distant galaxy, it becomes more noticeable that you've shifted into the red. But if you look at the most distant galaxies, the galaxies that formed at the very beginning of the formation of our universe, really distant galaxies, it's extremely noticeable how far they're shifted into the red. And so these first galaxies are the reason we built James Webb Space Telescope. We wanted to be able to image and take spectra of the first galaxies that ever formed in our cosmos after the Big Bang. And so where do we have to look? In the red. That is why we built JWST to be an infrared telescope. So here's a cartoon showing you the venerable Hubble Space Telescope. For those of you who don't know, the mirror of Hubble was built over by the Danbury Fair. You're using all the JWST mirrors. I'll be like, ah. But this is JWST to scale. And you notice how different it is. First of all, it's got this shiny gold mirror here, which is made of segments. And the reason it's gold is not because we wanted it to look pretty or be expensive. Gold is a very good infrared reflector. And so when you want an infrared telescope, you want a gold-coated mirror. Another thing you might notice is this huge sun shield here, this big structure, and that is to keep the telescope in the shade because the sun and the earth and the moon warm it up. And remember what infrared light is? Remember from the mirror cats? It's warmth. What we're trying to measure is the warmth of the most distant galaxies in the universe. So we have to keep our telescope super cold, and that's what this 5-layer sun shield does. And also you'll notice there's no tube. This thing is sitting out there in outer space. And that's because the tube itself can be warm, and it would swamp the signals from those earliest galaxies. And so that's why this telescope looks really different from Hubble and from other kinds of telescopes. It's because it's designed for the infrared. Okay, so we had a lot of science planned for the James Webb Space Telescope. I'm not going to talk in detail about this cartoon, but I already told you the light from the first galaxies. That's what we were designing this telescope to do. But if you can see the light from the most distant galaxies, you can see all the galaxies from then to now. So another key science theme was how we build galaxies and how they evolve over time. And another science theme is in the local universe. We wanted to look at how stars are born and how planetary systems begin to form. And then finally, our science theme about, let's go back, where did it go? I'm having a lot of operating here tonight. It's all me, I just sucked it. Planetary systems and the origins of life. This is where my science came into the program because our planetary system, the solar system, was included in this science theme. And this is the science that we planned for over 25 years to do with James Webb Space Telescope. And so it launched on Christmas Day in 2021 from French Guiana. It was launched on an Ariane 5 rocket, which is made by Arianespace, which is a French rocket company. And so I'm going to show you a video of the launch, and you'll hear it counting down in French, because it's in French Guiana.
6, 5, 4, 3, 2, 1,
Our telescope is inside that thing. It's crazy.
Itself, James Webb begins a voyage back to the birth of the universe.
That lady right there. That's all of us. There he goes.
Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
There it is. So I was at the Space Telescope Science Institute for that launch, and I was so nervous, I could not sit down. I was pacing, and when we successfully launched, we were all very happy, but that was only the beginning, because this telescope was all folded up to fit inside the rocket. The little clip I'm about to show you is the view from the rocket after it separates and JWST is moving off away. It's still all folded up, so it doesn't look like the telescope yet. You can see the rockets firing there. And this launch was so perfect That is why we have extra fuel to be 20-year mission. So we were really very happy. That's our solar panel deploying. It deployed 3 minutes early, which frightened everyone. So off it went, and it started a long journey. So here is a cartoon showing you how the telescope was folded up inside the rocket fairing. And then after it separated, the video I just showed you, it began the long journey to what we call the Lagrange 2 point. And as it took that long journey, it unfolded in about 497 different ways, many of which were single point failures, which means if it doesn't happen, you're dead. So that took a month to happen. And I had a to-do list on my fridge. And every time there was a successful deployment, I would check off the to-do list and post it on social media. I was like, woo! And so we eventually did get out there to the L2 point. Here's a cartoon of where L2 is. If you draw a line from the sun to the Earth, and then go another 1 million miles, that's the L2 point. And we're in a little orbit around that point. It's a gravitationally stable point. It's very easy to keep it there. And it allows us to orient the sun shield, not like this, but actually like this. So that sun shield is protecting the telescope from the sun and the Earth and the moon. None of that light will ever fall on the telescope. And the telescope actually can go back and forth like this, and it can spin around like that. All right, so we have what we call the field of regard, is like a big donut shape in the sky, and then it tracks all around the sun, and so we can see the whole sky with JWST. All right, and so this is a picture from a smaller telescope, an infrared image of a piece of sky with a small telescope, a space telescope. And then this is what the Spitzer Space Telescope could see of that same field. And now let me show you JWST's image of that field. That is what the gain was of this telescope. Absolutely astonishing improvement in the quality of the imaging, and then the spectroscopy, which I will talk about as well. So we explored the earliest galaxies in the universe. That is what we set out to do. And so let me start with a picture of what that looks like. This is a picture of a cluster of galaxies. Remember that a galaxy is a collection of billions of stars, right? We live in a galaxy called the Milky Way. But this is a picture of a cluster of galaxies. Every fuzzy object you see here is a galaxy made of billions of stars. Anything that looks like this with these sharp, what we call diffraction spikes, that's actually a foreground star, all right? But anything that's fuzzy is a galaxy. And let me just sort of scroll in, I'll zoom in. This cluster of galaxies is so massive that it's distorting space-time. And look off to the side. Everywhere you look, you see galaxies, 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 everywhere you look. And some of these galaxies are incredibly faint and incredibly red. Those are some of the first galaxies ever to form in our solar system. In our cosmos, in our universe, not our solar system. And so I'm going to now zoom in on a couple of the galaxies here. Oh, before I do that, I want to show you what this field looked like to the Hubble Space Telescope. I'm being so careful about what button I push, because I don't want the system. Oh, there it is. That was Hubble. And so I'm going to go back. Oh, now we're going to have to watch all of, there it is. That's a Hubble image. And then you can see the JW image, how many more galaxies we pull out. And so now what we're going to do is pick out some of these tiny red galaxies that we know are the first galaxies that have formed. And what we're going to do is we're going to measure not just the pictures of these galaxies, but the spectrum of the galaxies. So this image, which came from this little guy here, which is just a dot, right? But there's some structure there. This is what its spectrum looks like. You can see hydrogen, which is the red line, and oxygen with the blue line. Think about that for a second. You're looking at some of the most distant galaxies in our universe, and you're seeing the molecules that are there. That is the power of spectroscopy. Now let's pick out this guy. He's actually a little bit older, 12.6 billion years old. And look at his lines. You see how they're shifted to the red? Now we're going to look at this one, which is, where is he? Where you follow the line. You can't hardly even see him in there. But look at his lines. They're almost shifted out of our range. And finally, a galaxy that's 13.1 billion years old. You can just barely see it there at the edge, right? This is real data. I showed you this cartoon before, you remember? But this is the actual data from James Webb Space Telescope. So we're actually seeing these early galaxies, and the first images that we got of them, where you're seeing this clumpy structure, they were brighter than we had expected, and they were clumpier, more structured than we expected. And so the first year of JWST, there was all kinds of articles about James Webb Telescope has broken astronomy, right? In fact, we actually, now that we've had the data for a couple of years and have really dug in there, we do think that our models of the earliest galaxies were flawed. But we're still not quite sure what is happening. We're not sure why they're so much brighter than we expected. It could be that stars are forming faster. It could be that there's more dynamics happening in the very early universe. But the exciting thing is that what we thought we were going to see is not what we saw. We like that in science, because that means you'll learn something when you figure it out. So we're very happy about that. All right, so this was something that was released just the 1st of October, so just a couple weeks ago, and it's another cluster of galaxies. What was really exciting about this cluster of galaxies, which is also bending space-time, that's why you see these arcs, this is called gravitational lensing. But this one had these 3 interesting blobs there. So I'm going to zoom in on that a little bit, make sure that you're looking at those 3. Those are 3 images of the same supernova, but they're just refocused differently. And we're able to use this refocusing to actually measure a supernova in a galaxy that's even further than the clusters of galaxies in the foreground. And we're using that to help us map out the expansion of the universe. And the expansion of the universe is linked to a property that we call dark energy. We don't know what dark energy is. It's some kind of force in the universe that is causing this acceleration. But these three refocused images of the supernova got everybody very excited about this particular observation. And so they're going to be watching that, and because supernovae change. They get very, very bright, and then they fade. So we're going to be watching to see how these change with time, to see if the properties of a supernova in the very early universe are different from the properties that we see today. We don't know the answer to that, so this is a really wonderful example. There they are, you can't see them. All right, so we also explored galaxies changing over time. And I'd like to start with this picture, one of the first images we released from James Webb of something called Stephan's Quintet. There are 5 galaxies here, 1, 2, 3, 4, 5. And they seem to be interacting with one another. That's what all the swirly stuff that you see is. But if you zoom in a little bit, you'll notice that this one looks a little bit different from the others, doesn't it? Can you see that? It looks more sparkly. You're actually seeing the stars in this galaxy, but over here, you're not. That's because this one down here, that's a photobomb. It's a galaxy that's in the foreground. It's not related to the other galaxies at all. It just happened to be in the picture. But these galaxies are interacting with one another. And this is a far infrared image where you can see this dust lanes of swirling interaction amongst these galaxies. And I particularly wanted to call your attention to this core up here of that galaxy. That core looks like a star. It's got those diffraction spikes. That means it's really, really tight and compact. What that is something we call an active galactic nucleus. There is a black hole embedded in the core of that galaxy. That material is just being sucked onto. And What was JWST's superpower? Not infrared. Infrared what? Spectroscopy. So we do infrared spectroscopy of this object. And here's what we see. When you are zooming in on the core of that galaxy, when you're right on this, now you're all saying, wait, you said it was a black hole. I thought the whole idea of a black hole was that it was dark. Yeah, the black hole is dark, but all the stuff around it that's, falling into the black hole is super energetic. And so the stuff is bright. And one of the big surprises of the stuff when we did the spectroscopy, and you see there's lines for hydrogen, which we expected, but you see this big dip here? That dip is silicates, that's dust. We're seeing the dust disk of the material that is falling onto the black hole. That's the first time ever that we have detected that. We speculate about it, but JWST can actually see it. And then when you look in the outskirts here around the black hole, you see things like iron, neon, sulfur, very interesting chemistry. So that's why we say this is the power of JWST, is the spectroscopy. That's how you learn what's really happening there. I like to show this picture. This is a Hubble image, the blue. That's the JWST version of the same thing. And just like those meerkats, what looks brown to Hubble, it turns on brightly because it's star formation that's heating up dust. So we're actually able to trace the star formation in this galaxy by looking at the infrared image with JWST. So lots of fabulous science trying to understand galaxies over time. The birth of stars makes some of the most beautiful pictures for JWST because the star birth happens inside dusty nebulae, and dusty nebulae are just gorgeous to look at. I'm sure you've all seen this picture, right? Called the cosmic cliffs. What this is actually the edge of a super giant bubble. And we're just looking at the edge of the bubble here. And way up there were some very young stars. And as they were born, they had a strong stellar wind that was pushing on the dust out of which they were born. And so they created a bubble around them of this dusty wall. But inside the dusty wall, the pressure of the wind creates new stars being born. Here you can see a new star being born. Here you see a bulge, but I can tell you that at the end of that bulge is a brand new star. And that's why it's pushing around it. And if you look inside this, then you see other places like that. Here, look at that one. You see a star sort of glowing outside of its natal cocoon. So I once saw an hour-long talk about this image. There's so much rich detail and so much to learn about star formation and the dust and how the stars interact with the dust. You see shock fronts here. See these shock fronts right there and there from this star? There's just so much happening in this image, and it's incredibly beautiful as well. Now, this is the shorter infrared wavelengths. When we go to longer infrared wavelengths, we can actually see inside some of those dusty cocoons. There you can see that one that I pointed out before, but you see it has another little neighbor down here too. And up here, you see brand new stars. You can see how they're blowing bubbles themselves into this dust. So this is a really powerful tool for studying how planets form in these dusty environments, how stars form and how the planets form around them. We'll just zoom in here. Why not? It's beautiful. I'm going to show you another two more images. This was our first anniversary image. It's a star-forming region called Rho Ophiuchi. It's the closest one to Earth, and it's only 390 light years away. That means the light we're seeing left that star system only 390 years ago, so well within the time span of human history. How old is Ridgefield? Ridgefield We're at over 300, so we're like kind of like on a Ridgefield time scale here. I just like zooming in on it because it's really beautiful. This particular star is the star that is creating this bubble. It's pushing out all the dust. And so it's a really gorgeous, beautiful image. And here's one more image that was released today. So if you aren't on top of things in your social media feeds, you're seeing it here for the first time. It just came out today, and it is another star-forming region. Again, you know, these new stars are blowing out this stellar wind that's pushing out this bubble. And what's really cool about this particular image is it's in another galaxy. It's in the Small Magellanic Cloud, which is a companion galaxy to our Milky Way, but it is another galaxy. It's not local in our galaxy. So the fact that we can see the star formation happening in another galaxy with JWST is just mind-boggling. I mean, people are going gaga over this image. My social media feed was blowing up all day today. And I think they even found some brown dwarfs. These are stars that are not quite big enough to actually create nuclear fusion and become stars. They're like bigger than Jupiter, but not as big as a star. And they think they could actually see some in here. I haven't yet found them in the images myself, but I'm just reporting to you what I read on Twitter today. All right, so that's as fresh as you get. Okay, so let's move on. Let's move on. There we go. Now I was just showing you how stars are born, but stars have finite lifetimes. They die. And stellar death usually is cataclysmic. There's explosions involved. Here's a picture of something called the Southern Ring Nebula. This picture was taken by the Hubble Space Telescope. So now let me show you the James Webb Space Telescope picture of this. Look at all the detail that comes out there. And I'm going to zoom in a little bit here, because I want to talk about what's happening in the star that is dying here, that created this beautiful nebula. If you zoom in on this, you're probably saying to yourself that there's the star, right? But when we look with the longer wavelength camera, with James Webb Space Telescope, I'm going to show you now, look what happens here. Did you see the star up here? This is the star that is exploding. This is a photobombing star just in the foreground, right? It's not related to the nebula. This one, it was invisible before because it's just, you can almost see it right there, but it's enshrouded in dust. The next layer hasn't blown off yet, and so you need to go to the infrared, just like with the meerkats. Remember the meerkats? So it's glowing because it's warm dust. And in fact, the really complicated nature of this, people have modeled it, and they think actually there's probably 5 stars that are all in there interacting with one another, and that's what gives it that really complex structure instead of just a perfect sphere. So, beautiful example of using JWST to learn something new that you had not expected. Okay, now I'm going to talk about the solar system. This entire program was planned here in Ridgefield, in my office at Sarah Bishop Road, in the north end of Ridgefield. As an interdisciplinary scientist for JWST, in exchange for working for over 25 years on the project, I was given 100 hours of guaranteed time that I could use for anything I wanted, and nobody could tell me no, unless I wanted to do something stupid like look at the sun, right, or Earth. We're not going to do that. But my program was designed to explore the solar system with JWST. And this is sort of a map of our solar system. And remember, here we're here at Earth and the Moon. And remember, we went 1 million miles outward, and then we had our big sun shield right here. So everything inside is off limits. No pictures of Venus, no pictures of Mercury. Someone asked, are you going to look at the sun? I'm like, no, I'm not going to look at the sun. So, but everything else is fair game, from Mars all the way through, all the way out to the Kuiper Belt where Pluto and Charon are. And 100 hours sounds like a lot of time, but that's a lot of territory to cover. And also, I was one person. So I put together a team, and I just want to share that all these people worked with me to develop the observations that we were doing. I was the lead, but Andy studied asteroids, Geronimo studied Mars and Enceladus and Europa, Saturn's rings were done by Matt, Lee ran the giant planets, and so on and so forth. So I just want to make sure I acknowledge my team because they did the hard work. I was the figurehead. Okay, so let's talk about it. Jupiter. So people ask me, why are you using our valuable James Webb Space Telescope precious time to look at a thing we've already sent like 6 spacecraft to, that we've orbited, that we have an orbiter there now? Why are you doing that? And the answer is, because James Webb Space Telescope is so powerful that we learn things that we never even learned when we were orbiting Jupiter. Let me show you an example. Up here in the north, you see this beautiful red glow. That's auroral emission, and we expected auroral emission, but the vertical extent was surprising to us. That's hundreds of kilometers of aurorae up in the extending upwards, both in the northern hemisphere and all the way down here in the southern hemisphere as well. And even more surprising than that was if you look at the edge of Jupiter here, this edge was supposed to be in shadow. For my astronomer friends here, the Terminator. There should be no light here, but you see that light. Do you see that? You see there's a glow here? And when we first saw that, people are like, oh, your telescope's just out of focus. And I'm like, no, James Webb Space Telescope is not out of focus. This is, what we are thinking now is that high altitude aurorae is actually, that auroral glow is actually being distributed all the way around the planet at the very high altitudes. And we can see it here because the shadow of Jupiter starts there. It's dark there. And JWST is the only instrument that has had the sensitivity to be able to see that faint glow next to the bright Jupiter. Even the spacecraft that were there, they weren't able to see that. But JWST's sensitivity is so remarkable that it can pull that out. So that was a huge surprise. And that was some of our first observations of Jupiter. There's much, much more, and I actually have a slide a little bit later. This is the great red spot. It's not red because what wavelength are we looking at?
Infrared.
Infrared, right. So it's bright because it's high altitude clouds, and that's why it looks bright in the infrared. I have a slide I'll come back to in just a few minutes. And there's also all kinds of thunderheads and storms that you can see here in the infrared. But I wanted to emphasize how powerful JWST's dynamic range is. So that's Jupiter, but in a single exposure of Jupiter, we can actually see this gossamer ring here. You see the ring? Did you know Jupiter had a ring?
Yeah.
Yeah, Jupiter has rings. All of the giant planets have rings, okay? And Jupiter's rings are 1,000,000 times fainter than Jupiter. And JWST can see both in a single image. That's amazing dynamic range. That's how wonderful the cameras are. And there's lots of other stuff. There's moons, little Adrastea. This is about 200 miles across, that moon, and very small. So great science in the Jupiter system. Picture of Neptune. When this picture appeared on my computer screen in my home in Virginia, I started crying. Because this was the reason that I got involved with the James Webb Space Telescope project, was to get images of Neptune. And these rings, remember, all the giant planets have rings? The last time we had seen this ring system was 1989, when Voyager flew by. It had been over 38 years, and I had been waiting for 38 years to see it. And there it was on my computer screen, and I just started crying a little. But then I'm like, wait a minute, this is amazing. And then I started jumping up and down, and I was scared. Oh my gosh, it's incredible. I picked up my cat, pulled my cat up. Look, it's Neptune great. And my mom was upstairs. She's like, are you okay? I'm like, yeah, Mom, come on down. Let's look at this beautiful picture. So we're very excited about this because we're with JWST now. We can see these rings. We can actually map out how they're changing with time because we couldn't see them. We tried. I can't, trust me, we tried with Hubble, we tried with Keck, one of the world's largest telescopes. We just couldn't see them. They were too faint. JWST, they just boom right out of the page like that. And we're doing spectroscopy of them as well to understand their chemistry. So I was super, super happy with that. And we're working on papers about that right now. This is a cartoon of the planet Mars. And Mars is really bright. And there was a little bit of pushback from the astrophysicists when I said we're going to look at Mars. And they're like, you can't do that. You're going to burn out our cameras. They're like, no, we're going to do it. So this is showing you a piece of Mars that we looked at with the infrared cameras. And this is a big basin called Hubble Basin. And if you look over here in this infrared image, and then in this longer infrared image, that's the Hubble Basin. And we were kind of befuddled when we saw this picture because we expected the sunlit portion of Mars to be warm. And then as you got away from the sunlit portion, it gets cooler. And that makes good sense, right? Warm, remember the meerkats, warmer is brighter, and then when you get away, it gets cooler. But then there was the Hubble Basin. And we're like, why is Hubble Basin cold? And after a whole lot of debates and dialogue and lots of emails, and what we figured out was it wasn't that it was cold. What's happening here is that at this particular wavelength of light, 4.3 microns, there is actually a carbon dioxide line. Remember the spectral lines I mentioned? And in the basin, which is a hole on Mars, there's a higher pressure in that area. And this particular line got broadened by the pressure, and so the light from the line got dimmer. So it was a pressure effect that was causing this faintness, not a temperature effect. And so the takeaway is that you have to be very careful how you interpret images. You can't just look at this and say, oh, that's cold, because it isn't colder. There's a higher pressure at the bottom of the basin. And so that was kind of fun. We didn't expect it, but it all made sense when we thought it through. But we learned some things. We also did spectroscopy of Mars, and we could see things like carbon dioxide. You can see water on Mars. They have water clouds in the atmosphere of Mars. Carbon monoxide as well. There's signatures of that. One of the things that the team is working on now is methane. There's a big mystery about methane on Mars. Some people see it, other people don't. Some spacecraft see it, other spacecraft don't. And we're trying to understand why that could be. And so that work is in progress right now. I'll have to come back in a year or so to explain to you what we have learned from that. It's given the quality of what we can do with JWST, I think we're going to have some very interesting information about that to add to the debate about methane on Mars. And just by the way, some people say the methane is caused by biology and stuff, and I'm like, no, it's not. It's just like natural processes. So something else happened a few years ago. We crashed a spacecraft into the moon of an asteroid. It was called the Double Asteroid Redirect Test. And what we were trying to do was actually move the moon of the asteroid, because we care about asteroids that might hit the Earth someday. And if they do, we want to find out before it happens and deflect them so they don't hit the Earth. And so in this test, this James Webb field of view is looking right in here at the asteroid. And this is a little video afterwards when you can see boulders flying off of the asteroid. You see the little bright things moving outwards? So we were able to do this. We almost broke the telescope with this one because throughout the whole 25 years that I was working on the team, they agreed that we could track moving targets, but no faster than Mars, right? But this asteroid was moving 3 times faster than Mars. And we made them track it. And the reason I'm only showing you half a picture there is because halfway through the imaging, they lost lock on it because it was going so fast. And it drifted. And so that's why we only have half a picture near the end there. And they said, never again will you track something that fast. And I'm like, okay. So, but we really stressed the system, which was actually the point of my program. My program was to do science, but also to see how bright we could see things, how faint we could see things. Can we look at Jupiter? Can we look at Mars? Can we look at fast-moving objects? That was all part of the program that I had. This is Saturn's moon Titan, taken with the James Webb Space Telescope, and also near simultaneously with the Keck 10-meter telescope. And these are similar wavelengths. And what I want you to notice is that on JWST on the 11th of July, we were seeing some clouds up here in the northern hemisphere. And just a few days later, they're much, much brighter. These are clouds of organic materials like methane and ethane and acetylene that are convected, just like thunderclouds. You ever seen thunderclouds on the Earth, the big water clouds? They have this huge convection, these anvil clouds. This is happening on Titan as well, but it isn't water. It's this hydrocarbons. And in fact, this moon, actually, we know that there are lakes of hydrocarbons. It has a whole cycle. Like you learned about the water cycle on Earth with the clouds and the water rains down and it makes the rivers and then it evaporates into more clouds and that's the cycle. The same thing happens on Titan, but it's not water. It's like gasoline that is raining out of the sky into these lakes of this hydrocarbon stuff. And so we're actually seeing the cloud activity with James Webb Space Telescope and with the Keck Observatory working together. This was one of the most surprising things to us. Saturn's moon Enceladus. I'm going to show you a little movie. And Enceladus is a pretty small moon. This is Saturn. And it's embedded in one of the rings, a very blue ring. And so when we zoom in here, this is our picture with James Webb Space Telescope of Enceladus. The moon itself is inside that, and everything that you see here that is blue is water. This moon was found by the Cassini spacecraft to have jets shooting out of its southern pole, but Cassini saw jets shooting off the pole inside the size of this blue box. With James Webb Space Telescope, we see that water extends for thousands and thousands of kilometers. In fact, if you look carefully, you see how there's like a black line here and a black line there, and it's blue on the inside here? When we take a spectrum, remember our superpower, spectroscopy, when we take a spectrum of all of this, all of it is water. Water everywhere. This little moon is just spewing out something like 72 swimming pools per hour, 72 Olympic-sized swimming pools to be specific, per hour of water just being blasted out of the moon, and we can see it coming out, and we can see this beautiful blue ring we now know is a water ring. And so this is a very interesting moon for what we call astrobiology. It has great potential because water is one of the key elements for life as we know it here on Earth. This moon has water, and it's spewing it out at prodigious rates. And looking at how much water we see from JWST, we can calculate the volumes based on the spectral lines in the spectrum. And comparing that with the Cassini data, we think that it's been spewing this water out for 25, 30 years. So if there is life in the ocean on Enceladus, it's possible it's being spewed out into the ring system around it. So we're pretty excited about that. People might be thinking, what about Jupiter's moon Europa? We looked for Europa to see if it had water plumes, and we saw none with JWST. And I hope I've impressed upon you how sensitive JWST is. Now, it's possible that Europa has sporadic water plumes. So we will be looking again, just in case. But to date, we haven't seen any evidence for water plumes at Jupiter's moon Europa. So it's interesting. Okay, so it's a brand new science. On the 1st of October, we released this beautiful spectrum of Pluto's moon, Charon. In the background is a picture of Charon taken with the New Horizons spacecraft. And what you can see on this beautiful spectrum, water ice, carbon dioxide, hydrogen peroxide, can you imagine? On the surface of Charon, and carbon dioxide. And interestingly, when we compare it with this purple line, which was the data from the New Horizons spacecraft, there's this offset here, which we haven't explained yet. I remember when I saw it, I said, what is that, you guys? Like, why isn't it lined up? And they're like, oh, yeah, viewing geometry, maybe. And I'm like, really? And they're like, well, we don't know. So, interesting, very interesting. And that was just published earlier this month. The very next day, this very interesting picture came out. This is an object called 29P Schwarzmann-Bachmann 1. I actually observed it earlier on in my career with ground-based telescopes. It is something called a centaur. It's kind of like a comet, but not really. It's kind of like an asteroid and kind of like a comet in between. And these are JWST images where you take it at a carbon dioxide line and a carbon monoxide line. And the fact that you're seeing this stuff moving on the sides, it's showing us that this is a cartoon showing you that there are jets of material, kind of like we see with comets. There's jets of material spewing out of this object, which was kind of surprising. And so, so that's a brand new result. And then the very next day, I mentioned that I was going to show you some more about the Great Red Spot. On the 3rd of October of this month, we had a paper, my team put out this paper showing you different images of the Great Red Spot at different wavelengths of infrared light. And I pulled this out because this is how it was spun in the media. It was a cold heart and patchy clouds. So the longer wavelengths, the center of the Great Red Spot of Jupiter is cold, it's dark. And this is really a temperature effect, not a pressure effect. But you can see other wavelengths, you see all this other interesting structure all around there. One of the things I would like this team to do, and they've been promising for a year now, and I keep saying I want to see it, by taking these different wavelengths, we can build up a three-dimensional map of the Great Red Spot. Tomography is what we call it, right? So we'll be able to sort of map from the bottom to the top and watch it change with time. They keep telling me they're just about really ready to do it, but there's always this little problem and that little problem. So that may be another thing we have to wait for the next talk to see this three-dimensional map of Jupiter's Great Red Spot. Okay, so JWST also studies planets around other stars. We call them exoplanets. These are planets that are not orbiting the sun. These are orbiting other stars out there. And there's a lot of different ways of studying them, but the primary way that JWST does it is it looks at the light from a star. It does not resolve the star like this. This is a cartoon. But it's showing you that as the planet crosses in front of the star, what we can measure is the light from the star dipping and then coming back up again. That's called a transit. And we can observe these transits at multiple wavelengths. Here's an example of one of a planet called WASP 39b. And if I zoom in on this dip here, you'll see that different colors have different depths. And those, you can invert that to get the spectrum of the object by looking at how much absorption was taking place at that wavelength. And so that is what they do. And this is the spectrum of 39b based on those transits. And you see this big line of carbon dioxide. Now, WASP 39b is a hot Jupiter. It's not a planet like Earth. But I'm showing this to you because we have a lot of familiarity with lines of carbon dioxide like this. One of the systems that you'll be hearing a lot about if you follow exoplanets with JWST is a system called TRAPPIST-1. It's not a star like the Earth. It's a red star, an M-dwarf star, and it has 7 planets that are all about Earth size. Now, this is a cartoon. We do not have pictures of them, right? It's an illustration, and I just want to say that loudly and clearly. These look like dots, and we learn about them through the transits that we observe, all right? But the question I will pose to you is, can we really differentiate between exoplanet conditions? The reason we like the TRAPPIST system is that these guys are close enough to their star that water is like steam, too hot. These planets are too far from the star. The water is like ice. But the planets in the middle here, they're just right. They're in the Goldilocks zone where it should be liquid water on their surface. But can we really see that with JWST? And I'm going to show you, as a comparison, some other planets, right, that we've observed in infrared wavelengths, and there's their brightness. And that's that big old carbon dioxide line that I showed you for WASP 29b. And this one has ozone, this one has a little water, and you know these planets. That's Venus, and that's Mars, and that's Earth. So with low resolution spectra, if you're lucky, you can pick out this and this, but if you're just looking at carbon dioxide, can you tell the difference between this dry, desiccated, cold Mars, or the hot, melt lead on the surface, thick atmosphere of Venus? You can't really tell that. And so my question is for the TRAPPIST system, when we get the spectra, are we going to be able to tell if it's Mars, is it going to be Venus, or is it going to be Earth? And the answer is, my friends, it's really hard. All right, so what is the atmosphere of TRAPPIST-1e, the one that's right in the Goldilocks zone? In this chart I'm going to show you, the red points are actual JWST data for TRAPPIST-1e, and the red points, look at them, they're kind of all over the place. And there's like, people actually are like, what are these negative numbers? How can it have negative light? Like, this is noise. You're seeing a very noisy spectrum, not enough signal to pull things out. And if there was no atmosphere at all, it would be this yellow line. And you know, kind of looks like that, doesn't it, right? And if it was an Earth-like planet, it would be the blue line. And you're like, if you just look at this part, you're like, woohoo, it's water, right? But then you look over here, and you're like, well, and then you look at this, and you're like, oh, wow. And so this is our best system, and this is what we've got to date. So in the coming years, there's just not enough signal here. So they're going to be looking, they're going to spend, I think I've read, 140 hours staring at that one planet to try to make these error bars get smaller and to see if we can really pull some signal out of here. But it's hard. Exoplanets are very, very hard with JWST. And I will share with you that when we started to build this telescope over 30 years ago, exoplanets had not even been discovered. This telescope was not designed for exoplanets. And so we now know of over 5,700 planets around other stars. Here's a cartoon from the Jet Propulsion Laboratory showing you there are thousands and thousands of exoplanets out there. However, to be able to characterize them within their atmospheres and figure out if any of them are habitable, it really depends on how big your telescope is. And so here's a little cartoon based on real data showing collections of stars relative to us and the Earth out to 30, 60, 100 light years. And this is a 6.5 meter telescope. That's how many are available to us with this telescope, JWST. That's why you're going to hear about the same names over and over again, because these are the ones that are available to us. But to truly answer the question, Are any of these worlds in our local neighborhood, are they inhabited? You can't just measure a scant handful. You have to measure a lot. And so, if you want to measure this volume, hundreds of stars, you need a 12-meter telescope in space with the capabilities of JWST. Now, we may not be able to do that, but we're working on it right now. That's what I work on now. I'm working to build the next telescope that goes from Hubble to Webb to something we're calling the Habitable Worlds Observatory. Now, this one is a 12-meter. We may not be able to build a 12-meter. When I've been talking with the engineers, they're like, we don't have a rocket very big enough, you know. And even if you fold it up, if we want to do this in optical wavelengths, like blue, like Hubble wavelengths, we do have to have a tube to encase it, and we don't have a rocket big enough. And people, whenever we talk about this, like, well, Starship will do it. I'm like, yeah, okay. When Starship starts launching on a regular cadence, yeah, we'll talk about it, and I'll be happy to launch on Starship. But we're working on this program right now. This is what we do. And its goal is to find habitable worlds and maybe even in the atmospheres signs that there could be a biological activity on that world. And to do that, you need a big telescope. So this is our current working model of the Habitable Worlds Observatory, and we are working right now towards a launch date of 2039. And that's how long it takes, people. That's a really fast launch date. All of our technical people get super nervous, you know, but we're like, this is what we got to do. It takes a long time to build these missions, and I like to show this sort of last slide to draw this home by showing this picture of me with my little baby Lucas in 2002, and this picture was taken the year I wrote my proposal to NASA to become a scientist on James Webb Space Telescope. And now here's a picture in 2022 of me with the same baby. And he's right here in front row, Lucas. And this picture was taken when we got our first data from JWST. So that shows you the time scale of building big NASA missions. It's generational. And the astronomy kids his age who are using the telescope now, they were babies now. And so, we don't build for us, we build for the next generation. So, what about 2042? I am not going to show you what we're doing. But I told you we have 20 years of fuel, so we may still be getting JWST data in 2042, and I'm hoping that we will have a Habitable Worlds Observatory. And you all have a role to play in that. If you want to see this kind of stuff, feel free to write to your representatives in Congress, to Tim Kaine and our other, that's Virginia, sorry. I live in Virginia now. Whoever the Ridgefield representatives in Congress are, write to them and tell them you support NASA science, and that will help us someday get this done. So, James Webb Space Telescope, sharing awesome science with the world, with you in Ridgefield. Ridgefield helped make this happen. The data that you saw in the solar system was formulated in my mind here in Ridgefield. I'd like to end with this quote from Carl Sagan because it kind of encapsulates something about these big missions. For all our failings, despite our limitations and fallibilities, we humans are capable of greatness. JWST is an example of that, and I have been really honored to be a part of this program for 25 years, a lot of which was right here in Ridgefield. So thank you very much. I think we might have time for a few questions. Yes?
As you know, my dad and uncle were very involved in astronomy at Bergen-Elmer. They, both of them said we don't need to send men and women anyplace. We're much better off with machines. You want to comment on that?
Sure. The question is about the role of humans in exploration versus the role of robotic spacecraft in exploration. They both have their role to play. We can do a tremendous amount of exploration in our solar system and with powerful telescopes beyond our solar system with robotic spacecraft like JWST and all the other NASA missions that we do. But at the same time, sending humans to other worlds, to the moon, that fundamentally changes our perception of what is possible. And so it's not a question of either or, it's a question of finding out what the right rules for human exploration are and what the right rules for robotic exploration are. I don't think we could cancel the human spaceflight program and still have NASA. I think that they're too intertwined. And I will share with you the Hubble Space Telescope. The reason Hubble is still one of the most powerful telescopes is it was serviced 5 times by astronauts who risked their lives to go up there into low Earth orbit and take out broken instruments and put in new instruments. The Habitable Worlds Observatory, we are planning that to be a serviceable telescope, so that if we need to pull out old instruments and put in new ones, we can do that. So we see the synergy of human spaceflight and robotic exploration. Yes?
What will be the cost of this next generation?
Yeah, the James Webb Space Telescope, what is the cost of the next generation on the habitable worlds?
And why do we just need NASA to do it? Why can't private enterprise, groups can?
Okay, so what is the cost and why does it have to be NASA? Why can't private groups do it? So the cost of James Webb is about $10 billion, and that includes all of the operations of everything that we do. And we learned a lot of technology. We think that the habitable worlds will probably be in the same ballpark of $10 to $12 billion. We're not building an infrared telescope for habitable worlds, and that added like a couple of $1 billion. It's very hard to do. We've already demonstrated the segmented mirror technology working in space. So that's why we think it's going to be about the same cost. 10 billion, 10 to 12.
10 billion to this world is nothing.
I know it's nothing, but and it's not in competition with other things that we all need. If you cancel something like habitable worlds, you won't get more roads and you won't get new health care. That's not how it works in Washington. That's why I work in Washington. That's where my office is. Your question, the second question of important roles. So I believe that this is the role of not only NASA. I want to be clear. JWST was not only NASA, the European Space Agency, they launched on the French rocket, they contributed an instrument, they were deeply involved. The Canadian Space Agency provided our guidance system. So it's an international endeavor. And we're doing that with, we're building those coalitions for habitable worlds, talking to ESA, talking to the Canadians, talking to JAXA. JAXA is the Japanese space agency. They were really bummed out that they missed out on JWST. They want to be a part of habitable worlds. The Indian space program is doing great work with lunar landers and exploring at Mars. So I don't personally see that philanthropy will solve the challenge that we're looking at here. I think it has to be at a national level scale. Like NASA and ESA working, and the Canadian Space Agency all working together. So that's just the reality as I see it. Yes, sir.
Sound. Where does frequencies come in understanding the universe? Because when you talk about spectra, one of the things new to me as an audio editor is spectrographic editing.
Yeah.
It's amazing to be able to see the sound where I could never see that before 20 years ago, right?
Yeah.
And I heard that there's a correlation between the colors that we see and the sound frequencies in the hertz. So because I heard Tesla say something like, "We want to understand the history of the universe, energy, frequency, and vibration," something like that. So what do you say about hertz?
Yeah, he's asking about frequency, hertz, sound, and how does sound relate to things in the universe. There are a couple of ways I can answer this question. Some people are using what they call sonification of astronomical data to allow people to experience that in different ways, where they're converting the brightnesses that we see into different pitches so that you can hear things. There are certain kinds of astrophysical phenomena that do make sound, like there's these black holes that are swirling around one another, and as they speed up, they make chirping sounds. There are things in the atmosphere of Jupiter as certain kinds of plasma move through the atmosphere, it makes audible sound. So sound has an important role to play. I think we tend in our field to focus more on visual because up until recently we had no way of sharing that kind of information in our scientific journals and things. Now that we can have data associated with papers, I think there's a different way that we might be able to represent some of this in terms of sound. So it's something that people are exploring.
Yeah, over the last 20 years, there's always been a constant sort of buzz of, is there another planet out there like in the Kuiper Belt?
Mm-hmm.
And there's been some recent discussion about how some mathematical models are suggesting that we may be getting close to where to look.
Yeah.
Is this telescope being used at all in that effort?
So the question is about a putative planet that's further out in our solar system, sometimes called Planet 9. And when we have, there's some lines of evidence by looking at some of the bodies and their orbits that are all kind of aligned in interesting ways that suggest there might be another body there that was perturbing them. And this telescope is not the telescope that we're going to use to look for that body, because this telescope focuses on very small fields of view. There are other telescopes that are being built right now, both on the ground and for space, that are designed to do wide field imaging, and they are the ones that we would be able to use to search for a putative Planet 9. The Roman Space Telescope is like a Hubble class, but wide field, and so that might be interesting. My organization is building the Rubin Observatory in Chile right now, which will image the entire southern sky every 3 days for 10 years and create this amazing movie of the sky. And if Planet 9's out there, I think Rubin will find it. And then if it is found, if it is true that there is a planet, then we could then point JWST at it to try to characterize it. But this is not a search telescope. This is a characterized telescope. So we have different telescopes that serve different purposes. So that helps. Maybe a few more. Yes, in the back?
So I know that you mentioned that kind of the creation of James Webb started before even exoplanets were officially discovered. And I'm assuming because it was still in creation, that kind of influenced some of the machinery and kind of how it was constructed and what to put in for some of the instruments. So I'm curious, first of all, how much kind of influenced it, but second of all, then how, if at all, you're kind of looking to accommodate that as you're now starting to look towards the Habitable Worlds Observatory of how much do you build ahead of time versus how much do you kind of wait to see if there's any new science that comes up?
Yeah, a good question. The question is how much our knowledge of planets, he's asking specifically about exoplanets, influences the design of the telescope as it's being built, as JWST was being built, and then how might what we know and not know affect the design of a future telescope like Habitable Worlds. So we started designing JWST in 1989. That was before Hubble was even launched. And the first exoplanets were discovered in like 1992. So they weren't part of it. But over the years, as we were building JWST, exoplanets as a field grew and grew and grew. And so certain characteristics of the instruments were designed to be able to do the transit work, that you had to have rapid readout of subarrays of the detectors to do the rapid timing. So that was built in because we knew it would be interesting. And there was also a device called a coronagraph, which was built into one of the instruments. Coronagraph allows you to block out, if this is a star, the coronagraph blocks out the star and allows you to image things near the star. It's a way of trying to image some of these planets. So that was built into the system. So we were making adjustments to James Webb Space Telescope instrumentation throughout the process to take advantage of that burgeoning field. And right now, with habitable worlds, we are just the starting point of designing the instruments, designing the coronagraphs and the tools that we're going to be using. And the more we learn, the more we refine what we're doing. Generally, there comes a point where you have to lock in your design, right? But we try to keep the flexibility as long as we can, because you don't want to like lock in a design and then, you know, delay for 5 years and then you got an old technology. So it's a give and a take situation for that. But thanks for that question. Yes?
When you were showing the clumps of galaxies, you said something about them being clumpier. What did you mean by they were clumpier?
Yeah, so the question is about those very earliest galaxies and what their structure was. And in our Hubble images of the very earliest galaxies that Hubble could see, they typically were just dots, single dots. But with JWST, it was like clumps of dots stuck together. And in some cases, like little lines of things. So there was structure there to be seen, which was a surprise, because we thought that they would be so far away, so small, we wouldn't be able to resolve the structure. And so the fact that we could see this clumpiness, and it was bright enough to see, that was what was surprising to us. It suggested that these stars that were making the clumps in the galaxies must have been brighter than our models suggest, or there must have been more of them than our models suggest, or something like that. And so that's what I was referring to, the fact that we could see that stuff when we didn't expect it. One or two more questions? We're almost out of time here. Yeah.
Could Webb detect geologic activity on planets and moons? When you showed the picture of Mars, with the exception of Hellas, I thought it was going to be pretty uniform because Mars is geologically dead. It looked uniform to me. Does that mean there is some, or could be some geologic activity on Mars?
So the question is, could JWST see geologic activity on Mars? Mars, I think what's more likely is that we're seeing variability in the atmosphere. And because we're sensitive to the clouds in the atmosphere, and there's water clouds and carbon dioxide clouds. So I think we're more sensitive to that than we would be to albedo features on Mars. And that isn't something that I would rely on JWST for, because we've got orbiters at Mars right now, and they can do a better job of mapping out the surface features than we can.
But for other planets or moons, would it be of any?
It's definitely for one of the papers that we did write was about Europa. I said we didn't see plumes on Europa, but we actually were able to map out geologic terrain on Europa, and with our spectroscopy, pull out different chemistry on different parts of the surface, and found one part of the surface that seemed to have very fresh ice, suggesting that there was some kind of geological perturbations happening on Europa for that particular moon. So within our solar system, absolutely. When we're talking about planets around other stars, none of these telescopes are powerful enough to resolve the planets. They're just points of light. And one of the things, I'm going to give you a glimpse into the future, because this is what we do at my organization. When Habitable Worlds launches, and some of those planets, if we find evidence for potential habitability on those worlds, water, clouds, what we want to do then is take a picture of it. Resolved picture. None of these telescopes are big enough to do that. You know how big it has to be? It has to be a telescope 200 kilometers across. And we are not talking about building that. What we are talking about is using a technique which is called interferometry, where you take a telescope here and a telescope 200 kilometers away, and you combine the signal from them so they're acting like one telescope. Now, we don't have that technology right now. We do optical coronography on a small scale, but to do it on hundreds of kilometer scale, we think we have to actually go to a different technology where we're actually using quantum entanglement between the two telescopes. Spooky action at a distance. It is amazing stuff. I barely understand this stuff, and I actually studied it at MIT. It's craziness to take, but that's what And so we're now working on really, we call blue sky, it's like, you know, thinking about the future. But we're actually talking about working with people to try to do this, to build an array of optical telescopes in the Atacama Desert that are hundreds of kilometers apart. That will allow us to image an Earth-like planet around a sun-like star and see if it has polar caps and continents and oceans, which would be amazing. And that's what the future holds. So I'm very excited about that. Thank you all for your patience.